it's just, you know, without glasses, it's much easier. God. All right. So where we're going into today is this is for the lectures for HVR110, the afternoon course, week 4, lesson 2. This will be y'all's in the afternoon, split up a little bit between Wednesday and Friday, while the night class is going to have more they're going to cover because they get 3 lessons tonight. Excuse me. So again, HVR110, going to be using the electricity handbook. Looks like this right here. And we're going to be in chapter 12, going over electronic control devices. So specifically, we're going to be seeing as far as the system is concerned and as far as what we're going to be covering. There we go. So what we're going to see as far as components and everything for it is we're going to be going into specific electronic control devices. When we're talking about electronics, we're talking more about the control boards, circuit boards, your high-tech kind of and stuff. What we're dealing with more on a regular basis nowadays, what's become mainstream, what used to be top of the line in the 90s was, hey, you have a control board and an air conditioner. And that was like, whoa, hold on a second. Now, you can't find one without a control board, and at least one, if not, 2 or 3. Depending on how advanced it is and what kind of heating and cooling system it is. There's a lot of different applications we have for electronic control devices and a lot of different things that they can do. But it's a matter of basically understanding, how to troubleshoot one of these control circuits, how to troubleshoot these control devices, and what to look for voltage, for resistance, everything like that. So, like I said, going to try and see if we can get some hands-on, but we'll see how that goes. It's just a matter of timing and figuring out what our capabilities are as far as what limitations we've got for people and all that kind of stuff. Because I keep hearing different numbers every other day. So, I don't know. I'll try to figure something out, but yeah, that's what I'm trying to do. So anyways, since we can't get our hands on with these control devices and everything like that, what we're going to be talking about is electronic control circuits. In the meantime, we'll just discuss them. But as soon as, like I've been saying, as soon as I figure anything out, I'm going to let you guys know, and we're going to get something taken care of. And my eyelash is being weird. All right. So electronic control circuits, a lot of things are having it, like it's saying, you're having it on refrigerators, you're having it in air conditioners, you're having it residentially, commercially, pretty much everything in between. You're going to have it for, all sorts of different components and controls. Because at the end of the day, the electronic control devices and the electronic control systems are extremely accurate, they're predictable, they're reliable, and they are energy efficient. So they're a lot more reliable, and they last a lot longer, and they require less electricity than a contactor over its lifetime, or just a relay over its lifetime. So now it's no longer getting to the point where it used to be a relay, a contactor, a transformer, 24-volt signal. That was it. Now you're having more and more controls in between in those steps. As the voltage travels, it goes through control boards, and those control boards are basically terminal stations that are saying, okay, I've got low voltage coming in, I've got high voltage coming in, all of this one board, and it's going to decide, depending on what kind of call it's getting from the thermostat, or from whatever sensor it's getting information from, that yes, let's turn on the heat, let's turn on the AC. It'll make the decision from that point. So that's what we're getting to a lot of times nowadays with these newer systems. It's pretty interesting, and it's going to change. It pretty much changes everything in concern to HVAC and our air conditioning systems. So, as far as components and everything like that are concerned, what we've got as a major one is a semiconductor. This is basically what allows for control boards and circuit boards and microchips and all that kind of stuff to work and operate, is the idea of a semiconductor. It's not quite a conductor, but it's not quite a resistor. It's going to basically allow for power to pass through in a very specific way that allows for electronic signals to more easily be controlled and interpreted, and allowing a system to pick up on those kinds of differences. So semiconductors, they work really, really well. But again, it's not like you're going to be taking out a semiconductor, troubleshooting it, looking at it. What you need to understand is that they're a component of our control boards. They're going to be a solid state device typically. So it's actually going to be like a piece, an actual component. It's not just going to be some, logic in the computer or something like that. It's actually going to be a physical part. So a semiconductor, it just, it's a new end kind of electronic, but it's not really that new. It's something that's just newer to HVAC. These two, though, you're going to see more and more diodes and rectifiers. Now, diode, you may have heard about before with something called a light emitting diode, or an LED, which is pretty much everybody's TV and computer and phone screens nowadays. Everything is going LED or LCD, which is liquid crystal display. So it's, LED is really, really popular, but a diode itself, all right, is just something that's going to make it so that current can only flow in a single direction. All right, we've talked about it before. You have alternating current flowing in both directions. It's going back and forth between positive and negative constantly. The one that goes in a single direction is DC current. So a diode, and then you've got it where a rectifier is very similar to it. They can work together, and they can actually change alternating current to DC current. Now, why is this important to us as far as HVAC technicians are concerned? Well, modern systems are using it where they take alternating current and they bring it into the control board. They bring it into that semiconductor device and everything like that. And then in that, they're going to have a set of diodes and rectifiers, and they're going to change that AC current to DC current. Now, here's the benefit of it. We talked about DC current before. The big disadvantage DC current has is it requires very large gauge wire to carry voltage a longer distance, and it requires it drops in voltage very, very rapidly, and it requires usually some sort of battery or source like that. With a diode, with a rectifier, with a converter or inverter, you've got it where you're going to be changing DC, AC electricity as far as which one is it going to be. You can change DC to AC, you can change AC to DC. It just depends on what the job is for the component. So for us with a diode and rectifier, what we're looking at is we're trying to see, is it able to actually change that AC to DC? That's usually the way that you're going to see it tested as far as inverters and everything like that. And what this allows for is DC electricity can incrementally increase much easier than AC electricity. AC, you've got where it's got to go along that big sine wave back and forth, back and forth. But DC, you just basically control the peak, and that's the top of the voltage, and that's all it's ever going to be. You don't have to control the top and the bottom and make sure that that wave is squished, basically, to lower the voltage. For DC, just lower the peak, and that lowers the voltage. So rectifying devices and these really nice control boards and everything like that, they have it where there's more control available for the systems, and they're able to have it where they can do multiple speeds. They can have more control over how fast is that outdoor fan motor going to be operating, how quickly is that compressor going to be operating. All of that's adjustable for those devices, which is really the nice thing about it. That's what leads to this new level of energy and efficiency we're seeing in air conditioning systems, is the use of diodes, rectifiers, inverters, converters, and basically using DC electricity to its best, you know, because of the fact that we're not running DC through the whole house, to the house or anything like that. We literally run AC all the way, except for the last maybe 4 feet of it is DC wiring. So it really doesn't need to have that massive cable size. It still is a nice, clean, crisp signal of electricity, and it makes perfect sense. A lot of times it's not even 4 feet. Sometimes it's like less than a foot, or it's inside of the motor itself. It will actually convert AC to DC electricity with a board inside of it. So we're getting to the point where everything is becoming controlled with boards, not just the major, you know, outdoor unit, indoor unit, but even your motors are having their own boards just for an indoor blower motor, just for a outdoor fan motor, and those will be built in and part of the system to control those speeds and options with it. So a transistor, only time you might have heard about transistors prior to this is maybe from, you know, hearing about a transistor radio from way back in the day. It was kind of the birth of rock and roll. The only thing you really need to know about transistors is 2 things. It's going to have, basically it's made of 2 types of materials, P-type and N-type, right? So, and then there's 2 different ones. There's the PNP transistor and the NPN. Here's how easy it is. P-type and N-type material, right? So PNP transistor means P-type material, N-type material, P-type material. That's your transistor. NPN, you've got N-type material next to P-type material next to N-type material. There's your NPN. Are you going to be troubleshooting these? No, not really. Are you going to be replacing them? No, not really. But you got to understand, I mean, look at the size of this thing. It is smaller than the size of a dime, you know, as far as that transistor is concerned. But it can do so much. It can really allow and control the flow of electricity to send signals for a system. This is what made it where a radio was no longer something that took up an entire, you know, cabinet in a living room. It was now in the size of your palm of your hand. The transistor allowed for that. It controls electrical flow very, very well, and acts as a good, you know, source of electronic control. Hence the name of the chapter. Cool. So triacs, these are weird. A lot of this chapter goes over terminology, and what it's covering with the terminology is making sure that y'all understand at least what the different components you're going to see on a control board are, but not really going to be troubleshooting it. So diodes, no, you don't troubleshoot those too often. Yes, now and again, older boards especially, you would. Modern boards, not as much. Most of the time, it's now what's called a black box method, where you test the voltage and the signal and the everything coming into the board, and then you make sure that it's sending voltage and signal and everything out of that board. So voltage in, voltage out. That's it. But understanding these components and parts makes it so that you can more easily look out for weird stuff. Because that's one of the tough things with these boards, is you'll have it where it leads to a very common problem, which is because they're operating on such slight differences of voltage, amperage, and resistance on those boards, just a little bit of change in electricity can make it so the system fails or doesn't work as well. And then a customer's calling saying, hey, my AC is not working or my heat's not working. And you get out there and the system's reset itself. Or when you take the cover off, you disconnect the power because there's a switch right there. And that power is disconnected and now the board resets itself. And so you turn the power back on, it seems to be working fine now. Understand that there's things like this, like triacs, that are weird and have to be monitored to make sure that they're working properly. Typically for a board, most of the time you're going to see it where if something fails, you will actually see burn marks or scorch marks or, a melted board. That's pretty much the most common thing you're going to be coming across for these. So, excuse me. So for triacs, again, good Lord. For triacs, again, the whole idea is it's electronic controls with 2 diodes in a single device, right? It's basically going to have, in your book, it's got a symbol for a triac and everything, but it's basically a switch is how it'll operate and work. It's going to allow for electricity to come in both directions, but then when it comes in the other side, it's only going to go one way until it reaches a certain amperage. That's what it's looking for, when a certain current level is reached at the gate. So when a certain amperage is reached, then it allows for power to pass both ways. Otherwise, the triac is sitting there saying, no, we're not letting power pass both ways. It's going to be shut off right here at this point. Any interruption to that path of power, to that wave of AC current, is going to shut down a circuit. Doesn't matter if it's at the very start of the circuit, doesn't matter if it's right after our load, right before our load, right on our way back to neutral. Anywhere along that path between power, our load, and neutral, we're going to have it where if we interrupt it, we can shut down that system. Whether that's a fan motor operating too soon, so for a furnace, gas furnace, you might have it where a triac is used as a furnace delay to make it so that the blower motor doesn't come on immediately. It only comes on once the heat exchanger is warmed up enough. So this is the stuff that we're trying to figure out with these systems. But these are the pretty cool parts of it. LEDs, like I said earlier, light emitting diodes. These are going to be our main thing that we have for for our TVs and stuff. But for us in HVAC, the light emitting diode is actually a part of our control board. It's going to be the main way that most control boards will communicate an error code. Now, I say most control boards. There are plenty of them that do it by like an LCD screen or LCD numbers. If you've ever seen those, you've probably seen them on an old digital alarm clock or any old digital watch. Those kinds of numbers, as far as the display on them and everything, is what these the LCD numbers look like. But the LED ones, how it's going to be operating is on the control board. It will be wired in to our different components and everything like that. And that's going to make it where we have the system will actually be able to tell it, okay, if this fails, blink this many times, do this kind of, that's the main thing that it'll do. It's going to have error codes with a blinking message. So typically, and again, depends on the manufacturer, I'm not going to say that every single time this is how it's going to be, but typically if you have an LED code, you will see it either for a furnace or an indoor air handler unit. You'll see it where on the outside panels, where you're going to take, you're going to take the panels off when you get inside and everything to the unit. Those service panels, there's usually a sight glass on those, a little cutout section with a piece of plastic over it, and it's lined up right over where the LED is on that board. Now, if you go to a system and it's failed, you want to look at that LED and you want to count the number of flashes, all right? Typically, it's going to be 2 sets of flash numbers. It'll be one of slow blinks, so it'll be like 1, 2, and then, so you'd have to count, okay, I had 4 slow blinks, I had 6 fast blinks, so 46 would be my error code. Again, some of them is going to be backwards. Fast blinks might be the first number, and the slow blinks might be the second number. It just depends on the manufacturer. But the main thing to understand is that the manufacturer is going to have it where this LED coding will actually allow you to troubleshoot a system easier, and it will start pointing you in the direction of the issues of that system without you having to, go into really crazy amounts of troubleshooting right off the bat. You walk up to the unit, and some of them it'll be, Now, it's not going to say replace the capacitor. It's not going to tell you what to do, but what it's going to tell you is what failed in the system. A lot of these systems are really cool nowadays where the control board will not only tell the LED, hey, here's the error code, it'll keep a log. And you can press a button on some of them, it'll say memory log or error memory. Some of them it'll actually, it'll post basically a set of lights up of each of the errors, or some of them it will keep a log where you can plug in a computer or you can access it on the thermostat and you can actually see, okay, when did this fail? What day did it fail? What part failed? And if you see for the last week and a half that every day at the same exact time, the same exact failures happen, you know, let's say, I had it one time, went to a house, I went through error code log after log after log after log for the last couple of days for that house, and every day it started off the same exact number of errors. It was blower motor didn't work, system overpressurized, blower motor didn't work, system overpressurized. It kept doing that back and forth, back and forth, back and forth. I'm like, well, okay, system's kicking on, but the blower motor's not kicking on. And then it overpressurizes, and then it's got it where I've got to, you know, shut down the system. So, or the system shuts itself down. And it would keep trying and trying and trying to fire up again until, you know, I would notice at the point where it was like 2 days prior to me being there, the customer had, you know, it stopped getting an error code because the customer was like, screw it, I'm just going to turn the thing off if it's not working. So that's the really, really nice thing about these new systems is that they can keep track of that information. A customer is not going to know what part of their air conditioner goes. They're just going to know that something broke in their house. They're not even going to know that their air conditioner's their air conditioner. They're just going to say something broke. Some people, that's just, you know, that's the minimum, that's the max, that all they've got as far as information for mechanical parts of a house, which honestly, not surprised. A lot of people don't understand the mechanical components of the house, except for one thing. They understand they're expensive. That's the only thing most people understand about. This is another thing that makes it so that, you know, you don't have to educate the customer as much. The system will now be able to make up for that lack of knowledge that they would have, or the lack of information that you might be walking into. Getting that extra information about how a system's failed, what it's done when it's failed, how it's tried to refire, how it's tried to reignite or to turn back on, that all plays a role in troubleshooting. Especially when it comes to things like oil and gas furnaces, when it comes to air conditioners and heat pumps, pretty much every piece of heating and air conditioning equipment, we've got to make sure that it's running properly. And if we've got these LED codes and all these really nice controls to tell us exactly what's been going on with the system, it makes our job a lot easier. Just because we're not having to, you know, play a guessing game or hope that the customer knows what they're talking about. So another thing we've got is a thermistor, all right? So a thermistor is a pretty simple device. It's an electronic component, and it's going to change resistance based on temperature. Now, thermistors are used in a lot of different settings and situations. Sometimes they're used as temperature sensors for overheating on a furnace to turn a system off in case that happens, or they're used for a boiler for overheating to prevent that from happening. That's a typical thing you're going to see thermistors used for, is for heating equipment. They're used as a safety sometimes. But for controls, we use thermistors in a lot of different ways. We'll have it where one of the most common ones that's happening nowadays is including thermistors throughout a home, right? So here's how it works. You have a thermostat, right? Everyone's got a thermostat somewhere in their house or somewhere where they live. They've got a thermostat. And that thermostat is what's going to control the temperature. Problem is where the thermostat's located. It's only reading the temperature right there. That's all it can read. So I've got uneven heating and cooling throughout my house. Well, here's what's going to happen. As opposed to having that uneven heating and cooling, now what I'm going to do is I'm going to include thermistors. I'm going to put thermistors into separate rooms all throughout the house, all right? And each thermistor is going to feed back a temperature or a signal based on resistance. Basically, it's going to feed back a temperature that's going to go to that thermostat. That thermostat's now going to know, okay, well, actually, this side of the house is getting colder, while this side of the house is still staying at temperature. And these thermistors, what they'll do is they'll actually be connected with zone control dampers to open and close airflow to allow for heat to flow out where it needs to go. So there's a lot of different applications for them, but one of the big ones, like I said just now, is zone controlled systems. They will use a thermistor as a temperature sensor for the room. That way, the only thing that really sets the temperature for the house is the thermostat, and the thermistors make it so that the system maintains that temperature in every room. You know, if you're working on a commercial business or an industrial building or something like that, and you've got it where, you know, you can get to the point with these thermistors that every office room, every conference room, every little set of cubicles and everything like that can have their own thermistor in theory and have their own temperature control. So you could have where, you know, people in, you know, one set of cubicles versus another, they can have completely different climates just because they've got different temperature sensors that they can, with the new ones, they can actually set the temperature with them as well, not just maintain that temperature. But if it's just a classic thermistor that's just to maintain that temperature, it's great for those large buildings because when you've got, the whole thing surrounded in glass, all right, depending on the time of day, there's going to be one side of the room and one side of the building that's always going to be way hotter than the other just because of the nature of how sunlight goes in the glass. And it's going to get that temperature up in that building. So it's one of those things that really plays a big factor for modern controls are these thermistors. They're very, very useful, and they can be used for a lot of temperature control and helping our systems maintain their efficiency and continue to work properly. So again, keep in mind, positive temperature coefficient increases as the temperature increases, and the negative temperature coefficient increases as the temperature decreases. So just depending on, is it looking for a temperature increase or a temperature decrease, all right? Either way, it's going to be an increase in resistance, you know? If it's a positive temperature coefficient, of course, it's going to look for an increase in temperature, so therefore your resistance will change with that increase. And if it's a negative, it's going to look for lower temperature, so as the temperature lowers, it will still increase that temperature or increase that resistance level. So again, electronic control circuits, like I said before, typically they're going to be DC electric. It's not going to be AC electricity flowing through all these little thin wires, these tiny little resistors and chips and everything like that. What it's going to be is you'll have some sort of rectifier where AC voltage comes in. Here you can see at the top 24 volts AC coming in at least. And then let's see, is there a 120 connection? I think it's right behind this. Might be our 120 volt AC connection. And you've got it where this is another one of those things I was talking about before, where when you have that change from AC to DC, you can get some advantages. You get cleaner signal. You also get it where the DC electricity, because it's not running long distances, can still use small wiring and small components. And because it's a crisper signal, you can have it where it's going to be using less electricity. It's the same idea with like computer or something like that. Computers, you would think, oh, they require tons and tons of amperage, but actually computers require a very, very, very low amperage. What they require is a lot of watts. The reason why they require low amperage and high wattage is because it's not so much that the voltage is going in at a very, very high speed or a high amperage rating. It's that the power is converting from AC to DC, and it's that consumption on the DC level that consumes all of those watts of electricity. For our air conditioning systems, this makes it where these boards have to be very, very consistent as far as their energy consumption level. You do not want to have a board that's, you know, sucking up power or anything like that. So typically they're going to be in a resting mode. They're going to get a signal still from a sensor of some sort, typically a thermostat, sometimes a humidistat. Just depends on what kind of system we're working with. So the main thing understanding here is we got it where it's, you know, again, AC to DC, and these control boards, all you're really looking for is you're not testing, you know, it's not going to get to the point where you have to test resistance across these resistors or anything like that. Because, you know, if you guys ever got into it, if you really got into control boards, you can get to the point where you learn about the fact that depending on a stripe pattern and everything like that, that will tell you the amount of resistance, the amount of ohms that are supposed to be across that resistor. You know, and if it's not, that resistor, got to replace it. That's what it used to be back in the day. It's not anymore. It's way too expensive as far as labor time, and it's a pain in the butt to replace one little resistor, and you might not replace it that well because these are put in by a machine. And I don't know about you guys, but I am not a machine. I am not a robotic, you know, exact, on the money, looking right out the factory kind of guy. I've never been that way. It's always been a little bit, you know, wabi-sabi. You know, so it's just a pain in the butt. So just buy a new control board and makes your life a lot easier. You don't have to worry about handling a solder gun or anything like that. So I do like those. So again, simple electronic temperature control circuits. These are what we're talking about with a thermostat. A thermostat is a typical, basic, simple electronic temperature control. Now, thermostats can be used for, you know, making sure that the temperature of the air in a room is warm enough or cool enough. That's typical for comfort cooling. But we're also seeing thermostats are going to be used for a refrigerator. It's got a thermostat. The thermostat is inside of the refrigerator, and it's going to set the temperature of that air inside there, or a freezer will do the same exact thing. Those are still thermostats. They're just for a different purpose. We have where a thermostat that's used to test the temperature of a boiler, as far as the water temperature, is called an aquastat. And that's going to be to make sure that we have the correct temperature in that boiler as far as the water goes, make sure that it's hot enough, is an aquastat. So just like thermo, but instead of thermostat, instead of thermo, we're going aqua for water. So that's all that is. So how a typical switch is going to be working and everything like that. So let me see if I can get this to come up easily. All right. So you'll have it where you've got a switch. All right. And we're talking about a temperature switch. So this right here, what I'm drawing, is temperature closing on a rise. That's a normally opened switch. And this is a normally closed switch for temperature on the rise. So what happens is for a thermostat, as far as its typical operation will be, this point right here, all right, what this adjustment is, this will be literally a piece of wire for your most basic mechanical thermostats. It'll be a piece of wire or a conductor of some sort that'll be connected to a knob, all right? As I turn that knob, I'm going to move this, and that's going to, and that knob is the temperature, all right? So if I move the temperature down, let's say a house is 69, all right, and I want the furnace to kick on, all right, if I turn the temperature down, that's going to move this switch up, all right, it's going to move it further away because now this is going to have to rise less, it's going to have to wait a long time to get above that temperature. Basically, this would go past it. Sorry, this would go past that side. But for the for most thermostats, what it's going to be operating is it'll have where so you'll have it where temperature switch closing on a rise. As the temperature in the room increases, all right, this is your call for cooling. This is what this is going to work as. You'll have it where as the temperature rises, all right, this switch will then push up and then we'll make contact and carry a signal to our control board saying, okay, we need voltage going to our our contactor to turn on the AC. For a furnace, you're going to see it where it rises, where it's going to be a temperature switch again. It's going to be normally open, but it'll, oh my God, my doodles are so bad. It's going to be close on a fall, all right? So a heating thermostat will close on a fall in temperature. And this is, if the room starts getting colder, that's a fall in temperature. That would make sense. Okay, turn the heat on as it gets colder. If the temperature rises in a room, turn the AC on. That makes sense. So close on a rise is going to be for your cooling. Close on a fall will be for your heating. That's the easy way to think about those two. But that's what you're going to see a lot of times for these kinds of circuits and everything. All right, I'll go ahead and I'll upload this guy.